Hello, Augies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with another episode of Ask Dave. Our question today comes from Monty Bates, and it has to do with the designations of the various ham bands. Why do we call it 80 meters and sometimes 75 and things like that? So I thought what we'd do is start with this question and then, as usual, expand way beyond that to take a look. It's really kind of interesting to do. I've always wanted to do this exercise, and today I got to do it. So let's jump in. Monty Bates is KF0GPX, and he's a patron, and he put this on the patron bulletin board for me. It says, Dave, during my study of the General Class License Manual, I've noticed that General Class has access to 75 meters, which he here designates 3,800 to 4,000 kilohertz. One of the study questions is, which of the following frequencies is within the general class portion of the 75 meter phone band? The answer is 3,900 kilohertz, and that is not the problem. My problem is that I don't see 75 meters on the ARRL US amateur radio band chart anywhere. Can you enlighten me just a little bit? Well, I won't stop with a little bit. We'll go quite a bit beyond that. But here's what he's referring to. This is the 80 meters on the ARRL band chart. It shows 80 meters. It shows the starting frequency of the band. Okay, and it goes from 3.5 megahertz to 4 megahertz. Okay, so we're going to figure this out and see what's going on here. Let's, first of all, take a little bit of a digression to go over some of the things that we're talking about. Meters and megahertz band designations are definitely confusing. What we're going to look at is the actual relationship between the modern bands and the definition of the band in meters, wavelength in meters. The relationship between them, now this is for meters, megahertz and meters, okay, and that 300 comes from the speed of light, which is 300 million meters per second, and we'll talk a little bit more about that in a second. But you take 300 divided by the frequency in megahertz, and you come out with the wavelength in meters. And that is true in free space or actually in air, because the speed of light is very similar in both of them. If there is like a wire involved, you'd have to put the velocity factor in. We don't have to worry about that here. The definition of meter has changed over time. It was originally 1/10,000th of the distance from the equator to the North Pole on a line passing through Paris. This was back when the Parisians had a stranglehold on measurements and early science. Eventually, the British kind of wrested that away from them, and Greenwich Mean Time, noon at Greenwich Mean Time, is when the sun passes the noon point in Greenwich, England. So, now the distance of the meter was then figured out very carefully by a lot of scientific experiments and the best people in all the countries in Europe and the U.S. And it came out to be, it's the distance between two fine scratches on a temperature and pressure controlled platinum iridium alloy bar. And the iridium really strengthens the platinum. And one of these that was made was given to the U.S., and that served as the U.S. meter. And the people at Paris were in charge of doing this for everybody. Now, they've changed the definition of a meter. Not by much, mind you. Now, right now, it is the distance traveled by light in a vacuum in 1/299,792,458ths of a second. And that happens to be the definition of the meter in terms of the speed of light. If you take the speed of light and you clock it out, and you clock out 1/299,792,458, you'll get a meter every time. Now, this is in objects at rest and all of that sort of thing like that. Or if you round that off, it's 1 over 300 million. Okay, that's where the 300 comes from in the equation that we had right here. Okay, so what's a second? Well, it used to be a second. You take 24 hours, okay, multiply that by the number of minutes in an hour, 60, multiply that by the number of seconds in a minute, and you'd come up with 86,400. So a second was 1/86,400th of a mean solar day. But the problem is that the Earth wobbles. It's precessing. Gyroscope thing. Anyway, now we have changed the definition of the second. It's trying to be more stable than the Earth's rotation. Now, the duration of a second is exactly, by definition, 9,192,631,700 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Now, where do you come up with some cesium for your home clock? Well, you don't. What you do is you take the primary standard, which is actually averaged amongst several nations, the U.S. and France having the highest degree, and England have input to this. And so it's a number on paper. If you take like the atomic clock at the U.S., atomic clock at the Naval Observatory, the civilian time is kept in Boulder, by the way, military time in Washington. And you will get a definition of the second. So you look at your clock, and it will be 1/trillionth of a second later is the actual time. Okay, and then they send that standard out to people. Now, the primary standard is a cesium clock, okay? A secondary standard might be a rubidium oscillator or something like that. GPS actually is connected to an atomic clock. Now, GPS time is military time, but it's so close to civilian time it's not worth bothering with the difference. And one of the things I get in my little GPS clock is every second I get a bleep, and the bleep goes down to my little clock here, and so it's always accurate to well within a tiny fraction of a second. That's where we get time. We've got standards that go down until we get to the watch on our hands and so on. By the way, they have developed better atomic clocks recently that are so accurate that if they started counting time at the Big Bang, if that were possible, they'd be less than a second off today. That's how accurate they are. And so there is work afoot, but not yet complete, to update the definition of the second. No, you won't see your clocks change. It just stays that way. Okay, so that's a second. Now let's take a look at some of the bands. We're going to take a look at 2,200 meters all the way up through 70 centimeters. Here's a 2,200 meter band. This is a new band for us. If you take a look at 2,200 meters, it is 136.3 kilohertz, plus or minus a bit. Okay, so the bottom of the band, 135.7 kilohertz, is 2,211 meters. The top of the band, now remember as frequency goes up, the wavelength in meters goes down. So the top of the band at 137.8 is actually 2,177 meters. So we take this line, the red line in the middle, and 2,200, and that's what we call the band. Let's take a look at the 630 meter band. 630 meters is 476.2 kilohertz. Well, that's in the band. It's not exactly in the middle of the band. The middle of the band would be 631 meters. We could have called it the 631 meter band. 472 kilohertz is 636 meters. 479 kilohertz is 626 meters. Okay? So now let's go to bands we're more familiar with. The 160 meter band goes from 1.8 megahertz to 2 megahertz. In other words, it goes from 167 meters to 150 meters. And we call it the 160 meter band. Now, if we'd wanted to pick one endpoint, we could call it the 150 meter band, or the 165 meter band, or whatever. It's just we've got used to calling it the 160 meter band. Okay, here's the 80 meter band. 80 meters is 3.75 megahertz, which is right square smack dab in the middle. 3.5 megahertz is 85.7 meters. 4 megahertz is 75 meters. Now, although this is called the 80 meter band, and that point is square smack dab in the middle of the band, and some people might call 3.75 megahertz 75 meters. It isn't, it's 80 meters. The top part of the 80 meter band is often called the 75 meter band because the top of the band is 75 meters. Okay, now, you ready? Everything so far seems okay, but now we're going to get kind of whacked out. Let's look at the 60 meter band. The bottom of the band is 5.3305 megahertz, which is 56.3 meters. 5.4065 is the top of the band. That's 55.5 meters. So this could easily be called the 56 meter band, which would be a number right in the middle, but it isn't. 60 meters is 5 megahertz, which is way outside the band. Okay, so we just call it by convention 60 meters. 60 meters is quite a ways away from the actual frequencies. So if you're going to cut an antenna for that band, cut it for somewhere over in the middle here, rather than making it 60 meters. Okay, the 40 meter band is another one of these weirdos. 40 meters is 7.5 megahertz, which is well outside the 40 meter band. It's actually 42.9 meters to 41.1 meters, which is from 7 to 7.3 megahertz. This probably should be called the 42 meter band. But tradition, it's the 40 meter band. Oh, and it's just as whacked out at 30. 30 meters is exactly 10 megahertz. And in fact, if you tune into 10 megahertz, you'll tune into a true 30 meter wavelength signal on WWV. But our band up here is from 10.1 to 10.15, 29.6 to 29.7 meters. So it's a little far out to call it the 29 meter band. I guess 30 is close enough. Or you could go 29.65 or something like that. But we call it the 30 meter band. 20, the most popular band after 40 meters, is really whacked out. Look at this. 20 meters is 15 megahertz. Okay? That's nowhere near the band. It's a full megahertz away from the bottom. The bottom is at 21.4 meters, and the top is at 20.9 meters. We really should be calling this the 21 meter band, but we don't. We call it the 20 meter band. 17 meters, same way. 17 meters is 17.65 megahertz. The band actually goes from 16.6 to 16.5 meters. So you could use either one of those to define it. But people like nice even numbers, so we have the 17 meter band. The 15 meter band is really whacked out. Okay, 15 meters is 20 megahertz, and the band actually starts at 21 megahertz. It's one of our widest HF bands, goes up to 21.45. That is 14 meters to 14.28 meters. This by rights should be the 14-meter band, but it isn't. It's the 15-meter band. So let's look at 12. 12 is close. It goes 24.89 to 24.99 megahertz, whereas 12 meters is actually 25 megahertz. Okay, let's take a look at 10 meters. Oh, again, we missed it. 10 meters is 30 megahertz, which is not in our 10-meter band. Our band goes from 10.7 meters to 10.1 meters. Now, it's the middle point of that would be, let's see, 10.3, somewhere around there. And it's too hard to do. It's easier just to say 10 meters. And oh, heaven forbid, we should call it 11 meters. A long story behind that. 6-meter band is close. 6 meters is actually 50 megahertz. The band goes from 50 megahertz to 54 megahertz, which is 5.5 meters. So 5.5 to 6, we call it the 6. 2-meter band is another one that's whacked out. 2 meters is 150 megahertz. This band goes from 2.02 meters to 2.08 meters, and you could pick something in the middle of that, but it's easier just to say 2 meters. Because now we're getting down to the point where a big frequency difference, that's 4 megahertz right there, makes a very small wavelength difference. This is one of the reasons we don't use meters to designate which part of the band we go, because as you get up higher, a subtle change in wavelength makes for a big jump in frequency. Now here's a whacked out one. 1.25 meter band, this is our 222 megahertz band. 1.25 meters is 240 megahertz. This goes from 1.33 to 1.35. So if we're going to do this kind of thing, we ought to call it the 1.35 meter band. Or if we're going to go to 2 decimal places, the 1.34 meter band, which would put it right in the middle. But we don't. Okay, here is the 70 centimeter band, commonly known as 440. 70 centimeters is 429 megahertz. Now, 420 megahertz is 71 centimeters. 450 megahertz is 67 centimeters. See, we go across 30 megahertz of spectrum. This is one of our biggest bands. 30 megahertz of spectrum. Okay, and we only go up 4 centimeters in wavelength from one end of the band to the other. You see now why trying to get the meters accurate is hard. Now this is as far as I took it, because these are the bands most people use. But this brings up the question, why? And, why do we use these inaccurate meter designations for our bands? By and large, the answer is because. It's tradition. Radio started out on the medium frequency bands using meters or wavelengths to designate a frequency. Why? Because it was relatively easy to measure a wavelength. You just strung out a transmission line, okay, excited at one end, put a load on the other, and you could actually put a voltmeter on that line and slide it along the line until you go from the first positive zero crossing to the next positive zero crossing, and voila, there's your wavelength. You take out the 0.95 for the velocity factor, and you could determine wavelength very accurately. You could then convert that to frequency, but the speed of light was kind of still in flux back then. Now the speed of light was steady, but our measurements of it were pretty in flux. What happened was that the quartz crystal was shown to be a very stable oscillator. And so we started using hertz. Well, they called it cycles per second back then. And what's interesting about it is, like, a single sideband signal is 3 kilohertz regardless of what band you're on. Whereas if you try to do that in wavelength, the bandwidth is different everywhere. And so it becomes very difficult to deal with. That's why we use hertz now. By the way, those little quartz crystals were so stable that they showed that our definition of the second, which was 1/86/400th of a day, you know, what we think of as a second on a clock, varied too much from day to day to be accurate. And that's why we started looking for better definitions of the second. So the traditional band designations have now stuck. And this is what we've got now. If you look at the ARRL chart, these are the bands I went through down to here and here, and you could do the same thing on all these others. Okay? And I find it fascinating. The reason for this is embedded in our history. It's part of our culture as ham radio operators. So there you have it. A little bit of an exploration into ham radio history, poking at where these definitions come from, which of course is interesting if irrelevant to what we're actually doing. But it gives you some idea of why we call bands what we call them, what more accurate designators might be, but they'll never be adopted because we're so stuck in the way that we've been doing this for a long time. The bottom line is that there's a direct correlation, obviously, between lambda, wavelength, and F, frequency. And it's this 300 number if you're going to do everything in meters. If you do everything in feet, you need a different number, but you can do the same thing. The point is that there's a tight interrelationship. However, because of the sloppiness of early radio, the meter designations for the bands have stuck. And we actually, through history, our bands have been jockeyed around. And since they've been jockeyed around, they kept the same definition meter-wise, but it might have moved the frequency a little bit. So, there you have it. If you like what you're seeing here, please be sure to subscribe and click like. Also, if you would please take a look at dkassler.com/support and see if there's something there that might interest you. I also have some merchandise, which is listed below the video, like t-shirts and stuff. So until we next meet, 73.